Welcome to the MLIR Open Design Meeting. Today we have Martin Cole, who is going to present his work on interaction networks and the corresponding dialect. Martin, the floor is yours.
Thank you, Alex. Thank you. Yeah, let me share my screen. Okay, can everyone see my slides?
Yes.
Perfect. Okay, so thanks, Alex, and thanks everyone for being here. My name is Martin, and I'm a student at University of Buenos Aires. I've been working on an independent project on interaction networks, and I would like to show you what I did with MLIR. So in our agenda, we would like to understand graph rewriting as a framework in the context of MLIR. I will also show some discuss some prior art in interaction nets, compilers, and runtimes. And then we will evaluate the implementation of the Inet dialect. So I would like to start with graph rewriting versus term rewriting. These are alternative ways to work with formal languages. And in the last years, we've seen that MLIR grew as an option with support for graph rewriting at its core. It is this framework that is implemented via declarative rewrite rules using TableGen that allows us to express very concisely these frameworks based on graph rewriting. Let's start with interaction nets now. These are a computation model based on graph rewriting, and they are very general. We know from term rewriting systems such as the lambda calculus or Turing machines, we know through their conversions that they are as general, and so they can implement any kind of computer program. The interaction nets were introduced around 1990, and they are introduced as a graphical syntax for deterministic distributed programs. And they are both visual, so graphical as visual, but we will also take advantage of graphs, and we will work with this syntax in a formal graph rewriting based definition. I would like to now show these 3 images that I have here. Just very quickly, on the left we have. Let me go to the full screen. So many years ago, Lafon made these videos that explain. These are stop motion videos. Let's see the first one. So we see some kind of animation here. This is a representation of the visual calculus. Let's see that again. We have. Sorry, this is. Okay, let me try again. Okay, we see that there are 2 sides, they bump into each other, and something happens. Now, let's see another example. my God. Okay, I need to open files again. I don't know what happened. Let's see. The constructor is. Okay. And in this case, we see the same. These are this is another example of what a visual calculus looks like and how we should think about the rewritings. These are one-step rewritings. And these rules, these networks are built into some larger networks. So I grabbed this example from a different from another video, and here we can see a larger network, and the following animation will show how the network is reduced in several steps by executing some rules iteratively until the network is reduced to some other form, which is still a network in this case. But we see that this is a computation that progresses through graph rewriting. Let me show that again. We see there are 3 rules, and this shows the rules being applied to the graph. If we go back to the slides and we check the schematics here, maybe it will be simpler now that we have seen those animations to see what's going on. In the interaction nets, we will have just 3 types of nodes, which we call combinators. In these slides, each one of these combinators has inputs, outputs, or none. Or sorry, or one of those. We would take, for example, the example of meeting. Sorry, let me start that again. In the interaction networks, we have the combinators that form a network, and then we have the rules to evolve the network. These are all the rules we need in this calculus to give formal semantics to this calculus, and then apply it to an actual compiler. So the rules are called commutations when 2 different nodes bump into each other by their heads. So so you can see that the triangles on the left point to each other, and then something happens, and now we have 4 of these nodes. On the case on the right, we have this node, which just has one single wire connected to the other triangle, and the result of the rewriting is these 2 nodes that are now separate. The annihilations are similar. Sorry, the annihilations are similar. It's just another set of rules. Now, this is another schematic of a larger network, such as similar to the one that I was just showing, which was a larger network with some reduction steps. In this case, we can find many different places where we can apply reduction rules. So, so for example, this epsilon that bumps into this triangle that is connected here, that is one rule that we just learned how to apply. Also, we have these 2 triangles bumping into each other, and that is also another rule that we just learned how to apply. So this is a good moment to ask some questions, I think. Maybe this is the least known part of the talk, which is the actual interaction nets and combinators. Now we will move to more hands-on things.
Okay. Maybe before you do, since you're saying it's time for questions, I think it would be helpful if you explained what these symbols are. So we have triangles and circles with letters in them, but we don't know what they mean and what the connection between them mean.
Yes, perfect. That's great. So in the interaction nets, we have 3 kinds of nodes. We see here that they are red node, blue node, and a yellow node. We call the yellow node with just one wire and a eraser. That is the simplest of them. We call this this one the constructor. We'll call the blue one the constructor. And then we have the red one, which we call the duplicator. As I mentioned, these 3 nodes implement the whole paradigm of interaction nets. And the rules we define will, the graph rewrite rules come from these semantics of explicit duplications of every data that we need to duplicate, and an explicit construction as well. In this paradigm, when we bump them into each other, we will say that the constructor here, we see some kind of a C, and then here we have some kind of D for duplicator and some kind of E for eraser. Maybe that helps looking at these pictures. The image on the left is a commutation of a duplicator and a constructor. And in this case, we see that we get from two nodes, 2 combinators, we get 4. So in this case, the net is expanded. In this case, we have the eraser bumping into either a constructor or a duplicator. Sorry that I didn't mention that this alpha here is just either one. So in this case, we want to think that if you construct something or you duplicate something and then you erase, then that operation is like it never happened. And then we can tell the network that the replacement are 2 more erasers, and those will eventually interact with other combinators in the network so as to keep the computation moving forward. If we look a little longer, we will note that that these rewrites will preserve the number of inputs and the number of outputs. So you will see here that if we consider the 2 top wires as the input and the 2 bottom wires as the output, the whole interface is respected. The same happens here, where the output interface is empty. In the input interface is these two wires. So when we replace them with the erasers, and then the same happens in the annihilations, the interfaces are always respected. And this is very important for this framework because whatever happens when two nodes bump into each other will be a local interaction so that it won't affect the rest of the network. It doesn't matter which order we do the interactions. So it means that they are asynchronous and local. And those are really great properties for parallelism. So it means that we can easily parallelize whatever program is written using this formal language. Yeah, any more questions, please let me know. Here is a larger example again that maybe we can take a look at if there's more questions. Okay, great. So when talking about prior art, it's not easy to find implementations of this paradigm, although it has been around for more than 30 years. The currently most popular language is Bend, and the virtual machine and compiler, which creates an efficient CUDA runtime to evaluate these interaction networks. It uses CUDA, so a GPU acceleration that takes advantage of the parallel model of the interaction nets. And there is also the Vine language with the IVM virtual machine. And I would like to mention that some of the authors joined this call, so I really want to thank them. And the Vine language is their front end, and the IVM is their virtual machine. Both of these have both a front end, an intermediate representation, and a virtual machine. So we can think of them of each of these languages re-implementing the whole stack. Let me check the questions. Oh, hi T6. Thank you for joining. So these languages are pretty new, couple of years, 3, 5. Vine is much more recent, and in this language they have taken a lot of experience from previous work on HVM. I wanted to mention that although it's very niche and in a sense, we can see evidence in YouTube that there's a lot of interest for at least for unbounded parallelism, which is the promise that that Bend makes. And there are millions of people looking at this technology, although it's not yet available in any compiler or mainstream compiler like MLIR, LVM, else. Okay, so maybe now we can actually talk about this implementation of this as a dialect. So in MLIR, we have dialects, and I was I was surprised to find that what other times might be a 3-tier implementation of a front end, back end, intermediate representation, and so on, just like we saw before. In MLIR, it is much easier to reuse different pieces of the whole compiler infrastructure. So in this case, I was able to come up with a very lightweight dialect. It is standalone in the sense that it doesn't depend on other dialects. It doesn't lower into other dialects, and it doesn't use native types or advanced MLIR features, which I can mention attributes or regions. And I'm looking for feedback on this, because so far it seems that the core paradigm is really easy to implement and really well supported by MLIR. And it would be good to know moving forward what is the role of all these other features MLIR has that can be considered if this is added to the MLIR codebase. Okay, code. That's good. In MLIR, we have a intermediate representation like we see in the example. This is, I think everyone should be able to understand a simple function, which uses two of the combinators that we discussed before. The combinators are implemented as operations, which are one of the most basic constructs in MLIR. Operations like Inet construct here and Inet duplicate here. And these constructions take two arguments. The two arguments come from the function signature here. And they return one argument. So in this case, we are looking at the triangles that had two inputs and one output, which we call construct and duplicate. And just as an example, we can add those two numbers. So far, nothing too fancy. And this should be straightforward to anyone who knows programming. Now, when we get to the MLIR rewrite framework, we will note that it is a graph, a directed graph. We work with a directed graph and we perform rewrites there. And there are some other limitations that don't prevent us from implementing this paradigm, but make it a little bit harder. So in the case of matching the constructors, we weren't able to just use the operations before. And so we introduced the co-operation in reference to co-algebra. And these combinators allowed us to make it much easier to implement the rewrite patterns without any other additions or complications to the rewrite framework. Another example here, which shows the difference between the operation and the co-operation. In this case, the co-duplicate takes just one argument and returns two values. So this would be the upside down triangle for the duplicate node. So at some point we mentioned it was a red node, the red duplication node, but upside down. You'll see that the parameters are just passed. They are float 64s, but at any point we didn't actually use any typing, any type information. So this could be any type. It doesn't really matter. Defining patterns and rewrite rules is very easy in MLIR, and that was one of the things I wanted to validate with this development and original prototype. It promised to be very easy for implementing this graph-based paradigm, and I can see that it was. This is really just the whole definition of the rewrite rule for the erase annihilation. Let me just show you this annihilation schematically here. We see that we have an erase bumping into a co-erase, which is the upside down eraser, and that this gives us an empty graph, basically. And if we go to the slides, we see the same thing here. Erase and co-erase, and then just an empty result. As I mentioned, the erase and co-erase are needed so I can do this pattern where I only have just one root operation, and then I need to reference the other operation that I want to work with. If I didn't have this co-operation, it would be much harder to implement. We also have, of course, other patterns. All the different rules are here. Because we need to, for example, have co-construct arrays, but also co-arrays construct. So we need all the different combinations, which makes it a little bit harder to implement, but it's not too hard. It's just a little more duplication of code in this case. But we'll talk a little bit more about that later. Now, if we see this code where I use the erase and co-erase, we can see that the compiler will just delete those two operations because that was the pattern that we applied. And we also have a somewhat more complicated example, but it should be very straightforward if we look at the animations. We saw this first. We have the constructor and duplicator bumping into each other. So in this case, it will be a duplicator and a co-constructor. It could have been a co-duplicate and the construct, just keep that in mind. And we see here that the only parameter to the co-construct operation is the duplicate. So this means that the graph rewrite framework will be able to match this pattern where they bump into each other. And let's see what happens. Okay, we got 4 operations instead of 2. And you will notice that now the blue and red have switched places. They commuted. Blue is on the left, red is on the right. If you also look a little bit deeper, you will note that at the middle, we have a swap of these wires. So that's how the two sides are linked, not just one to each other, but also to the other one. If we look at the schematic, we have the left operation here. It's this commutation with the that we just saw the animation for. And in the case of the code, we will know that that the same is happening here. I want to point that the swaps are done by the indexing operations here. These are swapped by the rewrite framework, thanks to our pattern specification. I don't have the pattern here, but I can show it to you as well. So I have the implementation here. We can review the dialect code if you want. It's not much. All the standard rewrite rules are very simple, as you can see. Just a few ops, 1 or 2 lines. It's not hard at all. We were just seeing this one where we get a duplicate construct, and now we get 4 operations back. And here we have unit tests for each of these cases, which were also very easy to implement because it was a straightforward translation from the paper. So I just needed to write down the 2 combinators bumping into each other to and use the LIT framework in LLVM to test that the actual rewritings are as expected. For example, just to show something else, in this case, we just swap the arguments 0 and 1, and that is the whole result of this co-duplicate annihilation, and so on with other cases.
Interruption. There is a question in the chat
Yes,
asking.
Thank you.
Yeah, doesn't this essentially increase complexity of the program having more operators?
Yes. I will. Yes, I will mention that just a little bit, but the thing is that this is the actual computation. So when you perform these rewrites, the computation itself is moving forward, and so of course it will generate more interactions, and there might even be cyclical interactions or recursive. So you go back to the same original place. I will mention that in a few minutes, or maybe 1 or 2 minutes. Thank you for the question. It is the difference between how far we can get with these reductions during compile time versus what these interactions will do at runtime, which is 2 different stages that are not so hardly defined or so strictly defined, separated in this paradigm. So if I move to the future work, I would like to mention that as well. This is basically my presentation, and I want to mention some things that I think would be worth looking into. This pattern rewriting that I implemented doesn't terminate if this is a recursive one, but there exists this difference between normalization and canonicalization, so that we can find where to stop and avoid this kind of infinite compilation if the computation doesn't stop. Okay, so this means that these so this means on one hand that the blur the paradigm blurs the runtime and the compile time. This means that we don't have a runtime at this point because the graph rewriting only happens at compile time. You see that the results of the compilation process are still either operations in the same dialect or no operations because they were annihilated or something. But I'm never specifying what the runtime does. That is some benefit. That is a benefit of the MLIR framework, which allows me to just focus on the backend side. And when I was thinking that when I was thinking that the runtime can use GPU acceleration, well, I think it would be great to consider if the compile time can be accelerated through GPUs as well. And well, as I mentioned, there is no front end. So there's no front end language. So it would be also great to see this to see some language like Bend or Vine trying to compile to MLIR with this dialect. Lastly, the graphical monoidal languages are a much larger paradigm. One can understand interaction nets in the monoidal computing paradigm. And this opens the door to other calculus, such as the CX calculus in quantum computing. And monoidal languages are as easy as Inets. They are very solid mathematically. So it seems reasonable to think about further abstractions for these languages. So with that, I want to thank you for listening, and thank you.
Any questions from the audience? Okay, I guess not. So I would probably ask a very high-level question. It's okay if you haven't thought about it, but basically to me, this sounds like just a different abstraction for representing data flow in programs that would be competing with single static assignment that MLIR and LVM use. So the very high level question is, why did you even choose to implement this on MLIR, and what do you expect to gain from being based on it?
See. The idea is that the graphical language of interaction nets is not originally defined with the graph implementation, the graph-based implementation. That is something we can do when we implement that. And many papers after Lafont have done that and have helped implementing this framework. I think the MLIR compiler is the most advanced for graph rewriting, and the one that can easily support this paradigm. And I haven't found any other compiler that wouldn't I wouldn't be required to implement like primitive types, for example, or or any other, and many other things that one has to have in a compiler. With regards to SSA, I'm not completely, to be honest, I'm not, I had to sort it in a sense. I had to work around it, and that was why I came up with the coalgebras at some point. I think that was very helpful. But to put it simply, I think there was no better option for me, even when the SSA was in the way, and it didn't stop me. This was a prototype, and I think it was really good at the end. The results for me were very good. Maybe you have something else in mind. I would like to.
No,
To know.
I'm just generally curious. One comment I can make is SSA is literally what the name says. So it's a static single assignment. You can only assign once. In MLIR, we have two kind of regions. Both are SSA in the sense that you can only assign once. But there is a special kind of region called graph region where you can use a value before it's defined. Because you specifically mentioned reordering, just by using the right kind of region, you don't have an ordering problem because there is no order being enforced. You cannot use it in a function, you need to define your own container operation, but it's a perfectly supported use case, including in graph rewrites. SSA is really about signing only once. And here, at least what I could understand is you need to explicitly duplicate values, which to me sounds like that's why the question sounds like the opposite of SSA in the sense that it's a single static use. You cannot use the same value twice. If you wanted to, you would need to explicitly duplicate it, and like I relate that to some knowledge of quantum. So
Yes.
it says, yeah, there was a comment.
Yeah,
clarifying
Amar.
that. But generally, it pushes into IR paradigms that are different, and I'm trying to see. Basically, I have the inverse question as well. Like I asked you, why do you need MLIR? And the inverse question would be, why does MLIR need some of this?
Yeah.
Because to be completely honest, I sort of understand the concept. I don't understand what can I do with it. Like, how do I express a matrix multiplication? What it's good for? What does it help? How does it help with transformations? How does it help with performance?
I was going to ask
Nice.
if the folks that build HVM and Bend actually used MLIR in their process, and if they could actually maybe speak to that.
Sorry, was that a question for me?
I suppose so. If that's you.
Sorry, can you repeat the question? I missed the front end
Sure.
of it.
I'm just wondering, kind of in the terms of the applicability of Inet, did you use it to create Bend, and what was the thing that you found as a lever for it? Did you use it inside of MLIR, or is this a novel application of Inet?
So kind of to answer that, I'm the creator of Vine, and Vine has its own compiler and IR, etc. I think kind of this is I guess what I'm saying, I don't want to misspeak on Martin's behalf, but I guess kind of the way I would view it is, right now I have this IV language, right, which is this IR for these interaction net programs. And some various optimization passes on this that are all doing various forms of graph reduction. Some of them are just the basic, rewriting rules from the interaction nets. But you can also want there are more involved transformations that you might want to apply to these interaction net programs. And so I think the idea here, at least in part, behind using MLIR for the interaction nets, is being able to express a wider array of optimizations on interaction nets using MLIR and the infrastructure that's already there for, graph analysis and rewriting, rather than re-implementing it from scratch.
Yeah, that sounds very interesting. I think one caveat that I should mention publicly is graph rewriting infrastructure was mostly designed for sort of peephole optimizations that LLVM would have as inst combine, just at different levels. It's not really like there is a fixed point. There are several rewrite application algorithms that we use, but I wouldn't call it a full-fledged pattern rewriting infrastructure as one would expect in a functional language, for example. It can certainly be added, but it's not something the current one was designed for.
Got it. And with regard to your earlier point about the single static assignment, yeah, I do think it's a fair point to kind of say that, with these interaction nets, you have, I think it's kind of both single static assignment and single static use. And you get that from kind of the linear logic origins. So it's in some senses, I think, kind of assigning these operational semantics to linear uses of variables, etc., with these very minimal and these very minimal / simple operations.
Yeah,
One
okay.
question I have
Yeah.
for Martin, actually. Would you be willing to go back a few slides to where you had the example with like duplicate and construct? I think the first example of the Inet dialect you showed. Yeah, that one exactly. The operations example. Perfect. So like my question there is what does it mean that all of those are F64s, and what in the kind of interaction context does it mean to add A and B? You're muted.
Thank you. So the idea is that the values itself are the wires. So when you rewrite these operations, eventually you get a value of F64 that you can add them to. This is that you can add just like any primitive type, because you are constructing between two IRs. So I don't ever have to implement that addition, because I only expose the operations that perform the that abstract away the semantics, so that we can operate on the abstract structure of the operations graph. But in the end, for example, in this case, if this is not reduced and this is just a final compilation form of this, then at some point someone will have to assign some implementation to the construct and duplicate. But the reason that I find this framework interesting is that I can implement a single set of rewrite rules and leave this open for extension without really considering what the primitive type implementation will be. So users, so if someone else in MLIR chooses to implement a function using this dialect, and then someone else does the same thing in another dialect, those should be able to compose with each other using this framework. But in the end, everything just compiles maybe to LLVM in the end. So yeah, at some point the networks, the graphs have to run actual code, and that is derived from the rest of the dialects that implement, for example, native types or even GPUs or tensors. That's something that I'm really interested in. Because one of the questions by Alex was if this, how can this make things faster, for example? And the idea is that these operations allow one to construct distributed computation. How did I write it? Deterministic distributed programs, right? So if you are able to express some algorithms in this syntax, you can perform formal validations, and you can also guarantee that you will have the ability to run all of these reductions in parallel and locally, which is very, very useful in terms of implementing parallelism.
Maybe I have another question as well. The kind of linearity of interaction nets is also quite related to kind of the linear type system or ownership-based system Rust might have. Rust obviously uses LLVM. Now it doesn't use MLIR right now, but I'm sure there's people who kind of experiment with the ideas of porting ideas of kind of Rust into MLIR. And so I was wondering, maybe you, Martin, know something, or even Alex, if there are dialects being created which capture the ownership information, for example, of Rust programs, because that way might very well be an interesting dialect to then lower to kind of interaction nets.
Yeah, so actually somebody contacted me a couple of weeks ago asking to chat with people from the Rust community, and I completely forgot about it until now. I probably should, and I would know if they have something. Otherwise, I am not aware of any direct modeling, although we ourselves have discussed borrowing the notion of borrowing from Rust and having like owning and non-owning pointers on MLIR. Yes, so I understand there's a lot of potential here from different communities, and I'm trying to see. We also have 3 minutes left in the call, so I'm trying to see how to make sure people collaborate and can continue the design exercise here, so we can figure out how we can eventually bring some of these concepts into MLIR, potentially even as first class. I don't fully understand how it works and what it would require, potentially different kind of region or different kind of concepts. We can work with what's available right now and see if use cases appear that might be driving this. I suppose the question to Martin is, what are your expected next steps with this? And yeah, we only have like 1 or 2 minutes.
Yeah, no, I would like to continue exploring my personal project on hypergraph compilation. I would try to expand or continue with this with support with monoidal languages in general. I would appreciate like participating in the community and trying to provide some formal tools. I think these are like very interesting tools for the upcoming languages that I think we will see because of these parallelism features. and maybe work on a front end. I think something like translating or compiling Vine to MLIR. I would like to play with that, at least for to get more information and see how this might apply to the whole of MLIR, but starting with actually one implementation or one use case.
Yeah, I see. So in any case, you, as is everyone on the internet, is most welcome to participate in the community discussions, come present at this meeting. I'm trying to see if there is some help we can offer as a community, and it looks like at this point, if you have some specific design questions, feel free to ask those. If there is a group of people interested in developing a common dialect or common set of abstractions within the framework of the LLVM project, there are mechanisms to support that as well. They come with some overhead, so you need to write a formal proposal, get it accepted, discuss with people. There is an incubator mechanism in the LLVM where projects can go and just leave until they're ready to graduate. I don't know if any project has been removed from that, so basically just leave forever. It comes with some also expectations of the code quality. Yeah, I think it's the best, and like as you progress in your project, I'm sure we will want to hear about new findings, let's say in like 6 months or 12 months, I don't know. I think if folks from Wine are interested in coming and explaining how their IR works, even if it has nothing to do with MLIR, I think they would find an interested audience here, something to consider. And we can discuss, like eventually there is interested in porting to MLIR because there is something to be gained, like any of the abstractions we have or types or I don't know, distribution from borrowed from XLA. It's all up for discussion. Other than that, yeah, I don't have any specific suggestions or next steps I can pose.
Thanks a lot.
Okay, any last minute remarks? If not, then let's thank Martin for presenting. And as an announcement, next week we have the Euro LLVM developer meeting. So I think the open design call on Thursday will be canceled as people will be traveling back. And we will likely have a meeting 2 weeks from now. We do not have the topic yet. If somebody has one in mind, please contact me or just post a suggestion to the document. Thank you everyone for attending. Have a nice rest of your day.
Thank you, Alex. Thanks, everyone.